This lecture begins damped harmonic motion. This lecture is specific to AP Physics C and Honors Physics AB. There is no such thing as a simple harmonic oscillator. The reason for that is because, for example, as a spring alternatively stretches and compresses, due to molecular interactions that occur within the spring, energy is converted into heat. What this then means is that slowly over time, the amplitude of the oscillation decreases. Once again, this type of motion is referred to as damped harmonic motion. There is no such thing as a simple harmonic oscillator. So there are only DHOs, as we say, that is damped harmonic oscillators. The force that ultimately causes all of this, the actual mechanism itself, is actually quite complicated, but it does behave mathematically in a very simple manner, and overall, this is referred to as the damping force. Let me go ahead and retilt my phone, please, back to the board. All right, so bear with me here as I do. Like so, let me tilt it up as well. Okay, there we go. Okay, so now we take a look at the DHO, the damped harmonic oscillator. Okay, as I said, ultimately, as the spring alternatively stretches and compresses, energy is converted into heat. This is unavoidable. There's no such thing as an idealized spring. Okay, so there's no such thing as an idealized spring. As the spring stretches and compresses, energy is converted into heat. Okay, what causes this ultimately is just generically referred to as the damping force. So this is caused by the damping force, which results from the interaction of matter within the spring. Okay, the damping force is a type of restoring force. The reason why it's a restoring force is because ultimately what the damping force is doing is it's bringing the object back to its equilibrium position, and all of the energy has been lost as heat. So then therefore you end up with a total energy of 0. So the damping force is another example, like the spring force itself, is another example of a restoring force. Okay, as I briefly mentioned when I was demonstrating this a few moments ago, it turns out that mathematically describing the damping force is actually quite easy. It depends upon, directly that is, the speed of the oscillator itself. The greater the speed of the oscillator, the greater the interaction that occurs within the spring that ultimately converts the energy into heat. This then means that the damping force is directly proportional to the speed of the oscillator. Basically, the faster that the oscillator is moving, the greater the conversion of energy into heat. The damping force is proportional to the speed V. Once again, the greater the speed of the oscillator, the greater the interaction that occurs within the spring, therefore the greater the rate at which energy is being converted into heat. Okay, now when quantities, of course, are proportional to each other, this then means that empirically there is a coefficient that is present here that then turns the inequality, or excuse me, the proportionality that is, into an equal sign. This is referred to as the damping coefficient, and the damping coefficient is represented by the letter B. So the letter B is an empirical property of basically how quickly the energy is being converted into heat within the spring, and it's referred to as the damping coefficient. So even though ultimately the physics that's going on here as matter interacts within the compressing and stretching spring is quite complicated, physically, however, and empirically, mathematically, that is, it turns out that the damping force obeys some pretty simple mathematical principles. It's directly proportional to the speed of the oscillator. Basically, the greater the speed of the oscillator, the greater the rate at which energy is being converted into heat. And then the empirical property that describes all of this is called the damping coefficient. The damping coefficient is ultimately a function of what the spring is made of, for example, how thick the coils are in the spring, and so on. Okay, now when you include the damping force along with the spring force in F equals ma, you then end up with a pretty complicated differential equation. Here's what F equals ma looks like when we take into account the damping force. Okay, so first of all, writing it out, we have, first of all, the spring force minus kx, and then minus bv. The reason why, once again, the damping force is also considered negative along with the spring force is because, like the spring force, the damping force is trying to restore the object back to the equilibrium position. Okay, the sum of the forces then equals the net force, which is mass times acceleration. Okay, once again, this is not an algebraic equation, it's a differential equation, and because as the speed and position of the oscillator are changing with respect to time, the acceleration is changing with respect to time. Okay, here's then how we actually write the differential equation itself. I'm going to go ahead first of all and divide the mass m to the other side of the expression like so. And then right here is speed, which is the derivative of position with respect to time. And then right here is acceleration, which is the second derivative of position with respect to time. And then ultimately we end up with this expression here as our differential equation. So then what we have to do is we have to arrive at a solution to the differential equation. That is, what is a position as a function of time that fits into here? Its first derivative fits into here, and its second derivative fits into here, such that we then satisfy the requirements of the expression. So what is the solution x of t? The solution itself to the differential equation, as you'll see, is quite complicated, but it's easy to visualize why the solution has to work the way it does. The easiest way to understand what the function is that I'm about to write down is actually to graph it out first. So let me just go ahead and graph the function. You can almost see what the graph looks like here by just watching the oscillation occur once again. So let me retilt my phone here for just a moment. So bear with me here as I do. There we go. Okay, and then I take the DHO here and I send it into oscillation, and then slowly over time the amplitude is decreasing with respect to time. So ultimately what I'm going to draw here is just going to be a cosine curve, of course, but what's going to be happening to the amplitude of that cosine curve over time? It's going to be decreasing with respect to time, resulting then in the following graph. Once again, let me retilt my phone. And I'll tilt it up once again. So bear with me as I do. Okay, there we go. Okay, so the graph of the solution ultimately then looks at something like this. So here's our time axis, here's position like so, and I'm just going to draw here a cosine curve like so, but notice what's happening to the amplitude of that cosine curve. It is decreasing with respect to time. What you're seeing here is the product of two functions. The two functions that first of all describe the oscillation, and then secondly describe what's happening to the amplitude. Notice the amplitude is decreasing with respect to time like so. Ultimately, even though my drawing here is not perfect, the way that we mathematically describe the decaying amplitude is that it is in fact an exponential decay. So I'm going to draw a cosine curve here as I did, with an exponentially decaying amplitude. Realizing that the solution then therefore is the product of two functions, an exponential decay and also a cosine curve, leads us then to writing down the solution. So let me just go ahead and quote what the solution is to this rather complicated differential equation. I'll do so here on the bottom board. This expression here. So let me lead you through a brief description here of this expression. I'm not going to go through all the calculus that is necessary to show this. That would take the better part of about 45 minutes or so. But let me first of all just explain what you're seeing here with the function. Okay, this right here is describing the exponentially decaying amplitude on the graph on the top board. This is referred to as the amplitude term. The amplitude term is referred to as A of t. And then secondly, of course, we just have a cosine because after all, we're talking about an oscillation. So you end up with an exponentially decaying amplitude as the oscillations occur. Now the angular frequency omega. The angular frequency omega is not quite the same thing as it is for the SHO. Recall for the SHO, the angular frequency omega is the square root of k over m. That's not the case, however, in a realistic situation. In a realistic situation, the angular frequency also depends upon the damping coefficient. Once again, however, the angular frequency of the DHO, just like it was for the SHO, does not depend upon the amplitude. So then therefore we could use a DHO as a clock, that is as a timing element, as I already have previously described. But there is a difference between what really happens, that is the angular frequency of a DHO, and then what you approximate as the angular frequency of the SHO. For this reason, we actually now distinguish between these two quantities. We now sometimes refer to the angular frequency of the SHO as omega naught, and this is now referred to as the spring's natural frequency. Okay, now ultimately, where does this expression come from, the angular frequency of the DHO? Well, here's then how you would have to show where it comes from using calculus. What you would have to do first is you would have to take this complicated function here for the position as a function of time and fit it into here in our differential equation. And then you would have to take the first derivative of it. So that's going to involve multiple product rule and chain rule and so forth. You would then have to take the first derivative of this expression and then plug it into there. And then the situation gets even worse in terms of the calculus because you would have to take the derivative of that is the second derivative of the position as a function of time, and plug it into here. So it would take the better part of about 45 minutes or so for me to lead you through that, so I'm not going to bother to do so. But if you do all the necessary calculus by plugging in the position, plugging in its first derivative, plugging in its second derivative, then what comes out of the differential equation is this description here of the angular frequency. Much like, for example, that this equation here came out of the differential equation for the SHO. For the DHO, however, it's much more complicated, as you can see, and the angular frequency ends up being this expression here. Okay, now as we'll see in an example in the second half of this lecture, there's actually not much difference between these two values here, even when damping is taken into account. I'll get to that in my example, however, a little bit later on. One last thing, equation-wise here, about the DHO before we do in fact get to examples, and that's a description of its total energy. Okay, now to understand the total energy of the DHO, first of all, go back to the SHO. Recall that for the simple harmonic oscillator, the total energy is a constant. That is the following quantity, 1/2 Ka squared. I didn't do this at the time, but it's actually useful to graph out this function as a function of time and then compare it to what happens for the DHO. Okay, now for the SHO, if you graph out the energy as a function of time, because it is constant, you just end up with a horizontal line. That is like so, right here in the value of 1/2 Ka squared. Okay, what about for a DHO? While skipping over all of the necessary mathematics that is required to show this directly, you can understand what the total energy of the DHO is by once again just doing a 1/2 Ka squared type of calculation. However, the A in this case is the exponentially decaying amplitude. So then therefore the energy as a function of time for the DHO is once again a 1/2 Ka squared, but we now take this guy here, write this as A and square it. When you ultimately square this term, you then end up with the following. Like so. Notice the exponent here is lacking a 2, which was present here. If you take this quantity and square it, recall how you deal with that mathematically with the exponents. You just multiply them together. That is, you multiply a 2 by this 1/2 right here such that the 2 cancels out, and you end up with this expression here. Once again, to rigorously derive all of this requires a fair amount of calculus that I'm not going to bother to go through. Okay, now let's go ahead and graph out this expression that describes the energy as a function of time for the DHO, and just very simply notice that it just undergoes an exponential decay. So then therefore, as a function of time, the energy then looks like this. So right here at this point, when time t is equal to 0, you have e to the 0th power, which is 1, and then therefore the energy that you start with is 1/2 Ka squared. But then over time, as the energy is lost as heat, the energy as a function of time undergoes an exponential decay. So yes, I'm skipping over a lot of the calculus here in this lecture on the DHO, but basically what it boils down to is the following. You have an exponentially decaying amplitude as energy is lost as heat, which then ends up describing the energy being lost as heat as another exponential decay. That's basically what it boils down to. Okay, we'll take a look at an example in the next lecture.